Greetings and welcome to the Power of Vintage. Today's video is going to be a little bit different than my typical videos. In today's video, I'm going to talk with ECDHE, a friend of the channel, who has a tremendous amount of experience with how graphics work on various different machines, specifically talking about how graphics work on the Atari ST and how coders used lots of different fun tricks and what those tricks were in order to make the Atari ST do some pretty nifty things. All right, let's get to it. Greetings and welcome to the Power of Vintage. As you can kind of tell here, this is a little different format we got going on here. We have ECDHE who's joining us, and he knows a tremendous amount about Atari graphics, in particular Atari ST graphics, and he's going to share some awesome thoughts about that, how they work, how they function, and kind of give some really cool examples on how that goes. Laurent, ECDHE, tell us a little bit about your background. How did you get involved in Atari?
So I'm a software developer by trade, but I've been I've been in Atari for a long time. I had the what I call the VCS, what people call the 2600. I had the 800 XL as soon as it was available in '83. I had the Atari ST, the very first model in August '85. That is the one with the TOS on the floppy disk, with the external disk drive, and the easily accessible joystick ports.
Yes. Yes, you can easily plug in your mouse. You don't have to go underneath, lift it up, and look underneath in order to plug it in. Oh, yeah. That was mine as well. That was my first Atari ST as well.
But that was the very first, like the August '85. There was no software there.
Yeah.
On there, but so I've kept that for a while. I also had a second-hand Amiga 500.
Mm.
And then, well, in the 90s, I switched to PCs.
Yes, like most everyone did.
Because I saw the sign and said, okay. And for a few years now, I've been interested in retro computers, in particular, all those retro systems, how animation works.
Mm-hmm.
How is the hardware allowed to do animation on the various old computers, consoles? And I've done a bunch of systems, from the oldest one being the Channel F, the Fairchild Channel F, 1976, up to the most recent would be the Sega Saturn, from 94, and a bunch of systems, including some really obscure systems.
Now, when you look at that, I mean, there's a lot of variation, right? I mean, I think things standardized now more so, and were they very different? The application?
There was a standardization in '79 where you had four systems actually which worked very similarly. So the background is made out of tiles.
Okay.
Which is basically it's a glorified text mode where you can customize the fonts and you can have multiple colors on the fonts, not just two colors.
Mm-hmm.
And sprites, hardware sprites. And the idea is that you have the background that you can animate, and you have the sprites in the foreground, and that's the main. And there were four systems. There was first the TI-99-4, 104, in September. In October, let's see, there was this one. There was the, actually no, there was the Galaxian arcade.
Oh, okay.
That used that system.
Yeah.
With bidirectional scrolling.
Ah, yes. Side by side, upwards and downwards, yes.
Yeah. And actually, the very interesting thing, because the player does not move, it's scrolling.
I see. So the player stays static, but the screen moves. Ah, okay. Yeah. Very cool.
So there's TI-99-4, whose graphic chip was used in evolution in so many systems like the ColecoVision and others. Then there was the Atari 400, 800, which have also scrolling, hardware scrolling, and the Intellivision.
Yes.
Also released in '79. So all these use the same system, and you can be more or less sophisticated with hard scrolling or not, things like this, and number of sprites. But that's has gone through all the '80s.
Got it.
So this system has gone through all 80s, especially with Japanese computers and arcade systems.
Just more complexity, a little less complexity with the sprites and the scrolling and of the background as well, the tile scrolling.
Like some have like dual playfield, like the Genesis.
Sure.
So you have like the Capcom Play System, the CPS-1, released in what, 88, which is the Capcom system behind the arcade, like Street Fighter II, Strider, all these, which has like 3 scrolling play fields and 256 sprites.
Wow. Okay. And so that's just taking that original concept and just expanding it outwards.
Yeah. The Amiga took a different way. The Atari Lynx took a very different approach. The ST as well. So not everybody was like this, but that's been the standard throughout the 80s.
Sure.
And then you start having, in the 90s, you starting having 3D, and that was a very different system.
Yeah. Got it. Excellent. So you got interested in the retro. You started at the retro computing and how the graphics worked on them and programming in that space. What are some cool things that you've learned?
Well, it seems sometimes you see the evolution between systems.
Yeah.
Like you see a bit the evolution between the Amiga, the Atari Lynx, designed by 2 guys from the Amiga team, to the 3DO, designed by the 2 guys behind the Lynx, that is the late Dave Needle and R.J. Mikhail. Sometimes there's not much things. I mean, sometimes also before 79, you see it's like if you look at the Atari 2600, you look at the Channel F or others, it's all their own stuff, or the Odyssey 2, it's all their own thing. They do their own thing. There's no best practice yet.
Sure.
And so, I mean, there are sometimes also you find some obscure systems, like what's happening.
Yeah.
Or you look like the Atari Jaguar, which has a very unusual way of doing 3D graphics, very different than all the other 5th gen consoles.
Sure. So what did the Jaguar do differently? What was different about it?
Well, the first thing is that you don't draw all of them. All 5th gen consoles draw polygons. The Jag can only draw a line at a time.
Ah, okay.
So you do that first. First, you need to come up with your own routine to draw a polygon.
Sure.
One line at a time. And the Jag helps you, and it can be fast, but it's still you have to come up with your own routine. Second thing is that you need to deploy that code on the graphic chip named Tom.
Yep.
And that's so the code that displays a polygon and the code that displays all polygons needs to be deployed on that chip. But it needs to fit into 4 kilobytes.
Okay.
Because it's all that Tom has.
Yeah. Wow. 4K. 4K. That's
4K.
all Tom has. So do you just do lots of repeated instructions over and over again into that?
No, I mean, this is why you write it in assembly, because in 4K you can pack a lot in assembly.
Okay.
But this is where you will draw like all the code that is drawing first the routine to draw a polygon, and all the code that calls it needs to fit in the 4K.
Yes.
Sometimes you will need to deploy. To draw a frame, you'll need to deploy the code, and then you deploy different code to complete it. But a lot of times you fit it into 4K.
Yeah. Wow.
That's
cool. Those constraints obviously drive very interesting coding.
Yeah. It's also, I mean, they say is necessity is the mother of all inventions.
Yes.
Is that you see, like we'll see on the Atari ST, which has no graphical acceleration whatsoever. Well, people got creative.
Yeah.
And you'll find on some systems some things were very creative. There are some. I mean, I've done a few homebrew games on various systems, and some of them, my machine of predilection these days is the Atari 7800, which is also very different because it's guys who came from the arcade world. They say, we're going to design our own console.
Sure.
And they did. It was not made by Atari. It was made by a small company called GCC.
7800 was, really?
Yeah, absolutely.
It's not based on the Atari 8-bit at all.
Not at all. It has
Interesting.
nothing to. It's made by a bunch of MIT grads who started their trade by doing mods for arcade systems.
Okay. Yes. They're the ones that did Miss Pac-Man. Is that same
Yeah,
group? Okay, got it. So
they're
they
the one.
they did the 7800. Gotcha.
And that's why one of the first games on the 7800 was Miss Pac-Man
Got
or
it.
Foot Fight, which they did.
Yeah. Very cool. I did not know that. For some
Yeah.
reason I thought that the 7800 was
No.
just a growth from the Atari 8
No.
bits computers.
No, at that point, unfortunately, Atari had lost a lot of its talents.
Mm-hmm.
It says a lot about the state of the company when they have to call GCC to come up with some games and to come up with a next-gen console.
Yeah.
Atari cannot make a console and needs some help to make games. You're like, what are they good for?
Correct.
At this point.
Yeah, it was kind of it's interesting the whole corporate moves at Atari, looking at what happened, how it was founded, how it evolved and devolved over time. Yeah.
They started losing as early as 79. They started losing their talents.
Yeah. Mm-hmm.
Started with the 4 guys who left for Activision.
Yep.
And then they lost
Like Jay Miner going to eventually starting Amiga at that point in time, and then even more and more and more. Correct.
Yeah, and they still had some talents, but they started losing them. Mm-hmm. Jack Tramiel, when he bought Atari, brought back at least the hardware talent.
Sure.
He never brought the video game talent because he was not interested in that.
Yeah.
And that would hit Atari big time when they want to release new consoles.
Yeah. No, correct. Because you wouldn't have high quality programs, games to release with those consoles. I mean, the Nintendo, the original NES, right? They had a number of really good games that just came packed in. You know, Super Mario Brothers, amazing. Super Mario 3, this amazing game.
I mean, this is the difference with Nintendo and Atari. That Nintendo, they went first post-arcade. Mm-hmm. So first they created mascots, which Atari never did with Mario. Mm-hmm. They built franchises on top of those mascots. Mm-hmm. And then they went post-arcade.
Yes.
Something Atari never did. And arcade games have a very specific business model.
Mm-hmm. Pump quarters in. Keep people engaged to pump quarters in.
You need the players need to put quarters on average every 3 minutes.
Yeah.
Which means it's a fast-paced game. Mm-hmm. They're great arcade games, but it limits the style.
Correct.
And that's the difference between Mario Bros. And Super Mario Bros. The first one was an arcade. Yeah. Second one was not.
Correct.
It encouraged exploration, and Atari never had that. So when they released console, they never had a franchise to rely on when they released their game.
Yeah, we could go down that path. I've got some thoughts on that as well. I mean, I think it's fascinating how things moved and how the competition moved and how much evolution happened over time, over that short period of time. That's really, really cool. The console space, the computer space, it is so fun. Well,
they are.
Go ahead.
The history of all those retro machines, there are some interesting, like Atari history. The story of the Amiga is sometimes like insane.
Yes.
Involving like tagging the names of the CEO and chairman of the speed bumps of the company.
I didn't know about that part. I love it.
That's the last day when they went bankrupt.
Yeah.
And they set up on fire a figure of the CEO in the parking lot. I mean, Atari also has plenty of different things. So it's, but from a technical standpoint, I find it very interesting. You have not all systems are the same, and you've had very different things. And some developers have been very creative.
Yeah.
And typically hardware guys come up with something, and software guy says, how can we push the limit on this thing? How can we do things differently?
Well, you know what I love is, we live in today, I think the computing world is relatively mature. It's not perfectly mature, but I love looking back and saying, okay, so I use Excel a lot, I use PowerPoint, or I use these different tools all the time. How did it evolve to that point? And it's interesting to see some of the early starts with something like VisiCalc, right? And then how did it evolve into the various different features? How do they get added over time? I think that's really, really interesting. And the same thing goes, I'm sure, for the graphics guy as well, graphics capabilities, and how they've evolved over time and grown and changed.
Oh, yeah. Oh yeah, you have your various things, and so you have, especially like you have the big hitters. You have some lesser known but known systems, and you have, like I said, the completely obscure ones, which sometimes do things very differently.
Yeah. Yeah, I love watching, and there's some great. The retro community is awesome, right?
Oh, yeah.
And I love watching some folks who, for example, reviewing old Norwegian computers that were developed in Norway, small markets, but they built their own computers, and it's just amazing to see those things and kind of go through that history.
Oh yeah.
Well, how about we start going into a little bit about how do the Atari graphics work?
Absolutely, absolutely. So let me share my screen. Okay. Okay. So, can you see my screen?
I can see it.
Okay. So, we're going to talk about the Atari ST. And
I love the logo, by the way, in the bottom left-hand corner.
yeah, thank you.
Thank you.
I thought you would.
Yes.
So we're going to talk about ST and how some games are doing animation on that machine. Now, for the game, it's a selection between, so first it's 2D games. I didn't look at 3D games, but it's a selection between famous games and games that push the limits.
Correct.
There are some games which are famous but don't really push the limits. So now the ST has no hardware acceleration whatsoever, contrary to the Amiga. The Amiga has a bunch of them, ST has none. And they are basically two reasons, is cost and time. Everything I read from Atari at the time, they were under the gun. Atari was losing money, they need to release something fast.
Yeah.
And they did. They released the machine under a year, including porting GEM to the ST. So that was pretty impressive feat. So they did really well. The other thing is that it was custom chips like the Amiga would have been expensive. The first Amiga was very expensive. It was pretty much twice as expensive as the ST. The other thing too is that the ST was really geared against the Mac, not the Amiga. Its competitor would end up being the Amiga, but initially the target was the Mac. That's why it was dubbed the Jackintosh.
Correct. And I mean, that's why they had the monochrome screen with the high resolution. I mean, it was very much that way. Correct. Exactly.
It was clearly aimed, and when you listen to interviews from Jacques Tramiel of then, the target is clearly the Mac.
Correct.
Now, it doesn't mean that the ST is completely empty-handed, because it has, first of all, it has 500K or more of RAM. And that we'll see it will be used a lot for sometimes you have a speed memory consumption compromise. You will use some memory to speed things up.
Sure.
And also a very powerful CPU, which is the Motorola 68000 at 8 megahertz.
And at that time, that's pretty much top of the line in that 1985, 1986 timeframe. That's
it is.
Yeah.
So first of all, half a meg of RAM, that was huge. Remember, the first Mac was released by default with 120K of RAM.
Yeah.
And it cost $2,500.
Significantly more, absolutely.
So the ST was able to get sometimes better spec than the Mac for literally a third of the price. So let's see. So now, powerful CPU. Okay, what does it mean in practice? And this is where we're going to jump into an emulator.
I love this. This is awesome.
And first, run this program. So now, what does this program do? What it does, it has a bitmap that is copying line by line. So first it does is that it copies the top line, the bottom line of the bitmap at the top of the screen. Then wait for the screen refresh, then copies the bottom two lines at the top of the screen, and continues so on and so forth. So you'll have this scrolling ability at 60 FPS.
Quick question, is it supposed to be scrolling down the screen right now?
Yes. I paused it right now.
Oh, you paused it. Okay. Yes. Sorry, go ahead. Continue.
So the idea is that it's going to copy it. And the question is, how long until it needs to take two screen refresh to copy stuff? That will tell us how much can it copy within a single frame sync.
Got it.
Like, and if you look, you'll see there is a slowdown.
Yep.
Around 160 lines. Yeah.
There we go. Right there.
Yeah. And so what does it mean? It means that within a single screen refresh, so this is a program written in assembly, and I try to optimize it as much as possible. And that means, and you've done the same test of the same program on actual hardware.
Correct.
So you have a fluid 60 FPS at 60 seconds. Basically, I can copy 80% of the screen, more or less, in a single screen refresh. Now, this is an ideal scenario because here, first of all, it's a bitmap to bitmap copy, so that's easy. Generally, you have a tiling, your own tiling system, you have sound, you have the game logic, you have plenty of other things to animate. So 80% of the screen will be a really theoretical max.
Sure.
And yes, you can. I use the move.l assembly function, which there is a slightly faster way to move data, but
not that much more. I mean, it looks like just a smidge more.
Well, there is another way than move.l to copy stuff, but sometimes used. But basically, 80% of the screen, you'll never go that far. But
sure,
that gives at least an idea.
Sure, it puts a boundary condition onto what's the maximum.
Yeah, and so here we're gonna redraw. Okay, never mind. Okay, there you go. So now I try something here. So I try three-way scrolling, and of course on an ST it's not super fast.
Yeah.
As you see quickly, it starts slowing down very fast.
Yeah, at much earlier.
Yeah. Oh yeah. Not surprisingly.
But this kind of demonstrates an example of not just the scrolling, but if there was other logic going on behind the scenes. Any more complexity you add slows it down.
Oh yeah. So here, so that's for this, and you also run
on actual hardware.
This program on actual hardware. So people who want, they can go and pause it and look at here. So, yeah.
Gives you an example as to what else, what you could expect from real hardware.
Exactly.
Okay.
Now on to actual games. We'll start with Dungeon Master.
Love that game.
Now, Dungeon Master, it's not animation point wise, it's not like it's pushing the limits, but it's still like back then it's the killer game on the ST.
Well, I mean, it's not pushing the limits of the hardware. It's more of the concept and how it functioned.
Yeah, absolutely. I mean, it's animation wise. It blew everybody's mind.
Yeah.
Where you go, oh my God, I go use it. And it definitely influenced many other games. It redefined the genre. There's been first-person dungeon crawlers before. I mean, Wizardry on the Apple II, for example, Barksdale, but this one really redefined the genre.
Yeah. There you go. Uh-oh. It's going to get you. Close the door.
Yes.
There you go. I always love that tactic.
Yes. But, okay, so this is here. The one thing it has, of course, is that it's a game which is using a lot of assets. And we're going to look at that. So that's a program that I made, which allows to look at assets of a memory dump.
Oh, wow.
So you see here at the bottom, you have the frame buffer.
What's actually going to the screen, what you're actually seeing.
Yep. And you have here, for example, you have a bunch of different, like the characters, all the weapons, all that stuff.
Interesting. So, and you have all the different animations of the mouth, The eyes. Oh, that's
You have all the
awesome.
weapons, all these things, and
and you're just zooming out or zooming in, and so that's just stored. Is it stored in memory? Is that where it's at?
Yeah, it's in RAM, and this is where the ST with its 512K of RAM, because it can run on half a meg. It is useful because you have a lot of assets.
Yeah.
So you see here something, and you see here you go now. You see the monster closer and smaller.
Aha. So it's so it's actually not animating the monster. It's just pulling a different asset out.
Yeah, and absolutely.
Got it.
Which explains the blocky animation of the monster.
Yep.
And monsters will be loaded in RAM and unloaded from RAM as need be.
Got it. So you don't have all the monsters in RAM at any point in time, but each level has its own set of different monsters that are coming up. Got it. Makes sense.
And so you have here, and then you have over there. Let's see. There you go.
There's the walls and the tiles for the
wall,
the gate.
The gate, and you have the various kinds of wall to help make.
Make it seem more alive. So, a question for you. You know, one of the interesting things, mechanics that the game has is the lighting mechanic, right? If you have the torches and whatnot, are there different tiles for different levels of illumination?
I have not seen that, but it's easy enough to change the palette.
Okay. Oh, so you just change the palette. Got it.
You change the color palette. Generally, that's what you do because it's much faster. And so basically, you see here all the assets, and this is where the ST is really useful, is to have all these palettes, all these memory, because that's a lot of things.
And you can just draw it out as needed and bring it on the screen.
Exactly. So
Excellent.
that's for Dungeon Master. Now we'll move on to another game called Goldrunner. Keep going. And back then, the animation was fast. Was really fast.
Yeah.
You can flow really fast into obstacles. But it's extremely fluid.
Yeah.
So the game back then was like impressive. People did not expect to have such a smooth scrolling on the ST. And like I said, you can fly really fast into obstacles. Now, how did that work? Well, it's using, so let's go and see. So you have a few tricks. So here you have the double buffer. So it's using the common trick using a double buffer. So you display one buffer where you draw the other one. So you avoid any flickering.
Yep.
Once again, having a lot of RAM helps. So, but there are other tricks. So let me show you. So first of all, the full screen is 32K, less than 32K. But the area to animate is
a much smaller subset. Yes.
A very common trick used by so many games. You add a nice dashboard whose goal is to eat some screen state. Plus, you shave off a few pixels on the left, on the right, on the top, or the bottom, and you end up the area to animate of 58% of the screen. Much more manageable now. Remember, the theoretical max was
the animation, the scrolling animation, exactly. So you reduce the screen size to allow for the more fluidity. Yeah.
And the next thing to do here is that the scrolling area, if you only use 4 colors, you have the amount of data, like down to 29%. Now, why is that? So here's a little technical part of how color is encoded on the ST. So the ST is encoding by blocks of 16 pixels. And it's using mini bit planes, what is called. So the color is decomposed into bits So it's 16 colors, so 4-bit planes, and each bit of each bit plane corresponds to a single pixel.
Mm-hmm.
So to determine the color for here of this red pixel here, the third pixel, you look at the third bit of the third mini bit planes.
Yep.
So these are 2 bytes each. And so you end up, that's how you do. So this is an example. This is an actual memory dump of the screen of the play field of Goldrunner. You'll notice half of it is empty.
Intentionally. Again.
Yeah. Because if you use only 4 colors, you only modify the first 2-bit planes. So you modify only half of the data.
Yeah.
So that's half as less data to copy.
Again, and Enhance provides the smoother performance.
Yeah. Yeah, you have less data to copy, so you have performance. And I recreated that with this. So
oh wow! I mean, look. I mean, it's almost continuously smooth, right? You're not getting that slowdown, really.
Yeah. So I use the same assets as I took the assets from the game. I modified a couple of tiles only. You may notice those.
I like those. Yeah.
But the code is entirely mine. And I can go fast.
And you can accelerate, decelerate, but that allows for that again. You don't have those artificial limits coming in as much as you would like on the other examples that you're showing.
Yeah. So that's one trick I used. So that's one trick I used. Another trick is actually the encoding. And here is the code. Actually, no, never mind. It's not this one yet. So, but basically you have, so here are the tiles. So here the tiles look weird. But if I, hang on. Crap. I forgot to switch. Okay. Crap, is it here? Ah, yes. There you go.
There's the instructions.
Yeah. So here I switch to 2-bit plane, and you see all the tiles.
Yeah.
That's all tiles in the game. You have also the various sprites, also which are in 2-bit plane, so that's twice as less to copy. And this is why you have the game itself, which is a bit that's why like the background is a bit tame, because it's only 4 colors.
Sure.
It's a bit bland.
But again, it's the trade-off. It's that trade-off of performance versus quality, whatever. I mean, we still see it today, right? The whole thing with graphics cards today, you trade performance for quality.
Yeah.
Similar situation.
So that's what it did. Now, the next game we're going to look is Return to Genesis from the same author. So for those who don't know, so this Steve Back, he was the god of the ST, at least at the beginning of the machine. He moved on very early on the machine and did some amazing stuff. So here. So here. So parallax scrolling.
Yep. You more colors now, though. You also have a lot more colors. Now, it looks like you have 3 layers, or is it 2 layers?
2 layers. You have parallax scrolling, you have 16 colors, and horizontal scrolling, which is hard. And the reason it's hard is because, remember, and this is all machines in general, but like on the ST, remember, it's encoded in blocks of 16 pixels. So if I have my bitmap, I can copy it within a line. When it's not a line, it doesn't work anymore.
I see.
So I would need to go, if I want to copy this bitmap slightly shifted, I would need to modify 2 blocks of 16-bit pixels.
As opposed to 1 block if you're vertical scrolling, correct?
Yeah,
Yeah.
exactly.
So
One block
is
much
it is
easier.
it is it easy to say that it's just twice as difficult to do horizontal than
Yeah.
vertical? Okay.
Yeah. Actually, more than that, because it's not even copying, because I only need to modify only for the 2 pixels. I need to leave the other ones left. So I need to do a logical OR operation. It's really difficult.
Got it.
So first of all, as usual, small scrolling area. So you're 43% of the screen. Second thing is that, so here it has actually, the area to animate is actually 6x6 tiles. So it's tiles which are 6 blocks wide.
So it's pulling a bigger chunk
Yes.
out. And so it has more chunks to pull from, and it uses that trick. So you have different phases of that 6x6 or 6x6 chunk.
And so, and so this is by chunk. And the other thing is that it's using what would be called ugly code. And
Ugly code?
Well, as you don't need to know assembly to realize this is a copy of the same pretty much the same instruction.
Yeah.
Or very similar. That's the routine I pulled out from the game. That's the routine to copy a row. To create a row of data.
One row.
One row, like what's in red here.
Got it.
576 data copy instructions, not a single loop.
Wow.
Generally, what you do in programming is that you have a loop. Like you have a loop for 1 to 6 for each.
For 1 to 576, but in this case, you have individual data copy instructions.
So it allows, it's ugly code because it's hardly maintainable, but it's a video game. Who cares? It's the code will be thrown away, and it's much faster. So
interesting.
And there are 3 versions of it. Because depending on whether it's you have. So each, that would be one tile, like the 3 blocks. So when it's 1 block, 2 blocks, 3 blocks. So you have here also another example. This takes more RAM, but he doesn't care. He has enough memory.
So you're trading speed for RAM, for memory.
Yeah.
Storing more tiles, readily accessible tiles in RAM allows for you to move more quickly with that kind of coding.
Well, especially here, it's much bigger code.
Yeah.
The code itself is much bigger.
Correct.
So here's return to Genesis. So you'll notice also the dashboard looks slightly different. And it's because it's changing the color palette. So it has the color palette and it will change it mid-screen to have more colors on the screen.
Interesting. Okay. So what looks like just a gradient is actually a technique being used in order to adjust the color palette.
Yeah. So well, it will at the beginning of the screen it will set its given color palette.
Yeah.
Draws it, and afterwards mid-screen it will change it to be here. So here we see the color palette for the bottom of the screen.
Okay.
So that's a very common technique used. You'll see that used on Amiga. You'll see that used on the Atari 8-bit, on the Commodore 64, and many other systems where you will go and modify mid-screen the color palettes.
Yep.
And here are the tiles. And here's the trick. Here's another set of tiles. You notice the difference?
Yep, just slightly shifted.
So here's the trick. The parallax scrolling, it's just an illusion.
Yeah.
It's not actually
It's just
scrolling.
pulling different tiles in.
Yes. So this is how you're saying the example where you put more tiles, use extra RAM to have the pre-shifted tiles.
So let me just throw this out here. If you were able to, if a coder was able to optimize to leverage, let's say 4 megabytes of RAM on an Atari ST, you could have more capable graphics on an Atari ST.
Yeah.
Smoother, more beautiful graphics on the Atari ST by doing that, by allowing for more tiles to be stored in RAM to get that resolution. Very cool. Love it.
So here they are pre-shifted.
Yeah.
So they are pre-shifted by 1 up to 15 pixels. So all these things is dealt with because of this technique. Then all it has to do is to copy the tiles, which are then, like you have a tile like this, it's a simple copy from here, and it's aligned. They're properly aligned, so you need to copy them quickly.
Yep.
Using the quote-unquote ugly code that I showed you.
Yep.
And once again...
all those different copies.
Yeah. And I tried it. Well, this one, to make sure. And here it is.
You know, I love how you're recreating the code yourself to demonstrate it. I mean, this is fantastic because this is how you really learn, and you understand exactly what's going on behind the scenes.
Well, yeah. I make sure that it was working, and yes, and I can go fast. So yeah, that's how it works.
Cool.
And so I use the same similar code as Steve did back in the day to do it. But yeah, that's how it works. That's how you do the horizontal. That's how he's using the horizontal, smooth, fast scrolling with this a fake parallax.
But that's okay. You don't notice it. I mean, the end result is the same, right? For someone who's playing the game, you get the same result.
It looks, wow, parallax scrolling. It's not really, but it doesn't matter.
Yeah. I mean, so that would just suggest that, again, I'm kind of going back to if you had 4 megabytes as your starting point, or I mean, I guess that kind of explains why there's some limitations. If you're designing for the original Atari 520 ST, and you could have done more with a 1040 ST, just with double the RAM. You could interesting. Love it.
Because,
lots to digest there.
Yeah, because a lot of time they will pre-shift the tiles or the various assets. Of course, there can be combinations. So you could not pre-shift the ship with the background because there would be so many combinations.
Sure.
You would need like a Giga RAM. Yeah, with Giga RAM, yes, you could have all possible combinations that you just copied, but yeah, no.
But I mean, that's how you get more performance out of less capability. Love it.
Well, yeah. Now, next game we're going to see is Turrican II, The Final Fight.
And this is a beautiful game. On the Atari ST, I mean, it's beautiful. I mean, on the Amiga, it's beautiful, but it looks great on the Atari ST as well.
Yeah, Final Fight, because there's no other fight afterwards.
Yes.
So, Turrican, where are you? Here you go. Okay.
Oh, you died.
Yes, I saved at the wrong moments, but oh well.
That's okay.
So you have here bidirectional scrolling.
Yep.
And everything, I mean. Okay. Now, how does this work? So the scrolling area is quite large. It's smaller than on the Amiga, but it's quite large. You have 65% of the screen. Then you do a 30 FPS animation, which means you only have 32% of the screen per screen refresh to update.
Got it. Slightly less smooth, but 30 FPS in the 80s is just fine, or early 90s. Yeah.
So that's, so we're going to look, and there are other tricks. So Turrican. Okay, so you have the double buffer. You have the monsters, for example. You have a bunch of all the tiles, and you have pre-shifted buffers.
Slightly shifted, slightly higher, slightly lower, right?
Yeah. So you look here. So if you look here at the frame buffer, I did a memory dump at after several frames. So you see a bit the animation. So you see it's modifying one, drawing, then modifying the other one, drawing, and so on and so forth. But so it keeps 4 pre-shifted buffers. And here's what's happening. When you do, like here, it jumps up. And then it goes on the right. So it will go and copy those. So these are pre-shifted buffers which will be used to copy on the buffer. So it will copy that on the background and then copy all the, you'll notice here, it first copies the background and then, and then all the characters and everything.
Yeah.
And so here on the pre-shifted buffers, it has those because they are pre-shifted of 4, 8, 12. So 0, 4, 12, and 8 and 12 pixels horizontally. So that's how it's used to have, so that's why here the scrolling is not as smooth as that we've seen previously. But it's smooth enough.
The chunks are bigger chunks that they're shifting, the pre-shifting.
Yeah, exactly. So it's by 4 pixels, and it does it. So so whenever you go, it will go and modify those. When you go horizontally, it modifies all 4 of them.
And now you're going vertically.
Yeah. And when you go horizontally, it only modifies 1. So it will go and pre-shift it. So because the tiles here are not pre-shifted, as you notice, there's only one version. It will copy them, and here it will do the pre-shifting, and it will reuse that a lot when you. The reason it has those 4 is because you reuse those
over and over
very
again.
often. Yeah. And here, when you add a new column of pre-shifted tiles, you use the previous ones. So it's also, you'll notice it's a cyclical space. So the screen starts around here, it goes here, up, it stops, it loops around. But that's how it allows to have the animation.
Yep.
Which is fairly good. I mean, it's, like I say, it's not as smooth as we've seen previously, but it's still good enough.
No, absolutely. I mean, and it's just amazing what's being done with these limited resources. No acceleration.
Yeah.
It's still able to get this capability in play.
Absolutely. So that's for Turrican II. Now, we're going to look at Xenon II, Mega Blast.
Yeah.
Another
nice vertical scroller this time.
Yes. So,
I mean, this is a pretty smooth game.
Yeah. Beautiful graphics.
I'm assuming this is the full 16 colors. It looks like the full 16 colors.
Yeah. Like beautiful graphics, kick-ass soundtrack.
Parallax scrolling.
Parallax scroll, like, yes.
Vertical parallax scrolling, yeah.
Yes, vertical parallax scrolling, yes. So how did it work? Here, the animation area is huge. It's like 96% of the screen.
Yeah, the dashboard's tiny at the bottom.
Yeah. So here, what you're going to do? Well, how do you do that? Well, the first thing you do is that you have a 15 FPS animation.
Got it. So you reduce, again, by reducing the FPS.
Yeah.
It helps out. It enables more.
Yeah.
More on the screen.
Yeah. So here, here I took several memory dumps each time after each vertical blank. So after it drawn the screen, and you will see 1, 2, 3, 4. Now it's the bottom one. 1. 2, 3, 4. And on the top, 1, 2, 3, 4. So it takes 4 screen refresh, which gives it 15 FPS to redraw the whole screen.
Got it. Okay. As opposed to the full 60 FPS for the full screen. So this allows for more complexity beyond the screen at the same time.
And here's the background. Okay. And I'll split into. I'll switch here to 2-bit plane mode.
Yep.
And the background is in the 2-bit plane. It's 4 colors. So it's using the same technique as Goldrunner, that the background here, it's only 4 colors. So there is only 2-bit planes. There's twice as less to copy.
Correct.
But it's fine because there's so many other colors everywhere that you don't
overlaid
notice.
on the top of it, yes, so that you don't even notice it.
Yeah. If it was just this background, it would look bland, but because you have so many other colors there, it looks really good.
Yeah.
And so, yeah, that's how here the animation works, is that there is a lot of things. So if you look, once again, you look, first thing, it copies from the top. It modifies the top. It draws the top, and then it circles down, and then it draws all the characters on the screen.
The first fourth of the screen, second fourth of the screen. It's a quarter, right?
Yeah. And yeah, so that's how the animation is done. This one is like the FPS takes a hit.
Yeah.
Oh well.
But it's, I mean, you look at the gameplay, it's smooth. It looks smooth.
Yeah.
Play smooth.
Yeah. So that's for this. Next one I'm going to look is Pacmania, particularly the version for the blitter.
Aha.
The first version of Pacmania was just, was okay, but especially compared to the Amiga version, not great.
But this, getting blitter, having the blitter in there.
Yeah.
So this is, say, an NSTE or Mega ST.
Correct. And now you have
2-dimensional scrolling.
Yeah. And et cetera, et cetera.
Yeah.
Okay. So here you have the STE. So the STE had no acceleration whatsoever. The STE, they had the blitter as early as 87.
Yes, in the Mega ST first.
Yeah, it was optional. And it was really in the STE, released in, 89, I think?
It was 88, 89, yeah.
Where you have, so basically the STE is an attempt to catch up with Amiga. It does not have all the capabilities of Amiga. It has, I guess it's a catch-up, which is, I guess, in a way good enough. So it has the blitter, it has a hardware scrolling. The Amiga, on top of that, has the possibility to have dual play fields and as 8 hardware sprites.
Correct.
The STE does not, but it's still pretty good. So first, what is hardware scrolling? Hardware scrolling, the ability to have an image which is larger than the screen.
Ah.
So
you're
here,
basically taking a window and shifting the window around the screen.
Exactly. It's not the bitmap which moves, it's the camera.
Yeah.
And so it has a huge bitmap. You have the same thing on the Amiga. You have the whole maze is a huge bitmap, which is in RAM. And once again, having half a mega more is useful.
Yes.
And so that's how it works. So if we look, there are actually 3 copies of the bitmap.
Wow.
So there's for the 2 buffers and the reference, one for the reference.
What's the reference do then?
The reference is used because, remember, it will need to erase stuff, redraw stuff.
Got it. Okay.
So that's what you use the reference for. So you have here, and so it uses the blitter. The blitter is used for fast bitmap copy. So you see clearly here it has the screen, and so we're going to go, and first of all, it's got so here I stopped after X amount of blitz, X amount of blitting operations. So you still have a 60 FPS animation here, except here I stopped before that. So it erases Pac-Man, erases all the elements, and this is where it's using the reference. Because it used the reference to copy. It's a simple blit, and then it copies
everything else on top of that simple reference split. Got it.
It starts from the back to the front. There's not the ghost. He copies the ghost. He copies the health, and finally copies Pac-Man. and it copies the lives and the score.
Interesting. So, I'm seeing how that's being copied in there. The ghosts. Is the red ghost the base ghost, and then it's layers something else on top of it, or are there? Because
no.
Go ahead.
He can afford. I mean, the ghosts are not that much memory, so he can afford to have their own versions and stuff. That's not a problem.
I see. Okay, got it.
I mean, especially compared to the 3 maze beat maps.
Yeah.
the other assets here are just like ridiculously small.
Sure.
There's not much. So yeah, so that's how it will do. So the blitter on the ST is not as sophisticated as the blitter on the Amiga, but it seems to be as fast.
Sure.
At least it's fast.
Yeah.
And I tried to redo it a different way, actually.
Okay.
I did it. And here I did it by blitting everything. No hardware scrolling, I blit everything for every frame.
Oh. So what you're basically doing is you're just taking the camera image and shifting the camera image around the playfield.
No. Here I blit the maze. At every frame here, the maze is blitted, the entire screen.
Oh, okay. I misunderstood that. Very cool.
So here, I'm not using any hardware scrolling. I blit every single thing every time. And you'll notice it slows down a bit when there are several ghosts. It starts to slow down. So that, I tried to see, okay, how fast is the blitter? Now, of course, it's only an emulation, but still. And so I can... But this is a bit to show, like, the blitter can do quite a lot.
Yeah.
It's not... You will not have to can do everything and keep in 60 FPS, but still.
It can do a lot. It can actually do a lot of actions.
Yes.
Very cool.
So this is an example of the games here. So here, like in terms of blitting, there's not that much because thanks to the hardware scrolling on the actual game, you only have to blit the Pac-Man and the Ghost and the power gel. So it's not that much. Oh yes, the lives and stuff. So it's not a lot.
In this specific game. This
specific game. Yeah.
Correct.
And you will notice, so too, the maze on the reference, it removes the packs as you eat them.
Yep.
Because that's a reference. So when you need to redraw something, you need to redraw them.
You don't want to add the pellets back on.
Exactly. So that's basically how this game works.
Excellent. It's so amazing, right? So
yeah, a
few different games, just a few, and they're all very different. There's some similarities in how some of the applications and what they're using, what tools they're using, but there's a lot of differences too.
Yeah. I mean, the common thing would be use a double buffer, which is still used today, because you want to avoid flickering, so you display one buffer while you draw the other one. If you drew it in real time, it would
flicker.
It would look weird. It would flicker. It would look bad. So this is not all computers could do that, because some had the frame buffer was at the preset address in the hardware, and that was it. So you toast. Others you could do that. It depends on the systems.
Yeah.
But the double buffer will use, otherwise they will use different technique depending on what they want to achieve.
Yep.
And it's a trade-off, as you said. It's a trade-off. Where do you want smoother animation or more stuff on the screen?
Or more colors.
Or
any number of different things. More detail.
Yeah. So this is the whole thing. Now, it wouldn't be a Power Vintage video without talking about
you got to have the Ultima in the background. But I would expect this is a pretty simple game compared to those other ones.
This is the last Ultima to have been written on the Apple II. Because all of them, Richard Garrett coded it himself on the Apple II, and then it was ported to other machines. So for the few lost souls who don't know what it is...
I love this.
etc., etc.
Oh yeah. And then you have the different play fields,
Yeah.
the town play field, and then you have the external wilderness play field.
Okay. So, the game itself, so it's a bunch of tiles which are updated on the fly, but we can still look at it here. So you have the tiles. You see, so you have some things here. It's not super well, it's encoding. Encoding is a bit special. But I was able to extract, yeah, the encoding is a bit weird, so I don't see it, but I was able to extract them. And here are all the tiles.
There we go.
512 tiles. So 256 are the background, 256 are the various characters and monsters.
With different animations, right? So the animations are their own separate tile in that case, yeah.
Except if I took a snapshot at different time, and here's what I see. You will notice the water moves changes.
Ah, and the lava does as well in the different fields.
Lava, the flags fly, move. So this is because otherwise there would be way too many tiles.
Sure.
So it's much easier anyway to modify the tile than having to modify all the, especially when you have water, to modify everything.
Yep.
So it modifies the tiles every 4 or 5 frames, I don't know, but it will modify those tiles, and so that when it draws, it draws the animation. So that's this. Otherwise, when you are in a town or a castle, it's 32 by 32 tiles.
So every town or castle is the same size playfield. Yeah.
It uses a mini-map to determine what is visible and not.
Sure.
Because if you remember, here, like, well, I don't see anything.
This is a subset of the total screen, yeah.
First of all, it's a subset, and then on that subset, there's a part which parts of are hidden because the trees are hiding them.
Yep.
So it has a mini tile of 6 by 6 where it goes and says, okay, here's what you will see, and like of the tiles, just the tile map, a mini tile map, it does that. When you go outside, it's 4 quadrants of 16 by 16.
Yep.
So the upside is that allows the game to load things as you go. So you are like here, when you get closer, here, when you get closer, it can unload this image and load another one, another tile map, at least a tile map in memory.
Yeah.
And this is the whole world. I extracted it from the disk.
Now, when you look at this, I mean, if you're looking at a computer with significantly more RAM, memory, you can load the entire world or the majority of the entire world all at once.
Absolutely.
So when you play these games, like on a Commodore 128 to Commodore 64, you move so much, and then it has to access the disk in order to pull more information out, the new sets of tiles. Got it. Okay. And that's the whole world. Well,
that's the whole world.
Yeah. And there's black spots. What are the black parts?
So I took that straight from the disk.
Yep.
I extract that from the disk. It turns out there are some holes because it's called sparse tiling. There's no point in having any map here because it's all water. It's all sea.
It's all the deep water tiles.
Yeah,
exactly.
It's the deep water tiles. So there's no point in storing them on disk. It just marked, okay, this area. So thank goodness for me that they were stored sequentially. Except when I started drawing them sequentially, I realized that there's some problem. It's not aligned. And then that's where I realized it using sparse tiling.
Yeah.
So instead of storing everything, there's some stuff where it doesn't care because, well, it just marked them as it's all, as you said, deep water. So it just draws with a certain tile and that's it. But otherwise, that is the entire map that I retrieved from the disk.
That is awesome.
with all the details, which I'm sure you are.
I'm very familiar. Yes, exactly.
Yes, you probably know them by heart.
Spent a lot of time in this game.
Yeah. And because I could, I extracted all the other maps.
All the different town maps. Yep.
All the various towns and stuff.
Mm-hmm. And then the different floors, in like, for example, in a castle,
yes.
each floor is its own map, correct?
Yes.
Yeah,
so you have here, you have the floor, goes up, and yes, each floor is its own map.
Yeah.
And you have a bunch of them. You have this one where the 2 floors. A bunch of them, and there are some. Now, an interesting thing on this one. So you have the 2 floors, 2 levels, but if you notice, there are a few differences. Like here, the bridge here, or the cross here. When you go up,
it's gone.
Why should?
That must be a mistake, I would assume.
Yeah. Of course.
That is hilarious.
You are here, so you don't see them.
Yeah.
They're too far away, but the bridge disappears.
Yeah. But you would never notice otherwise because you would never see this.
Yeah.
Which is, I'm sure someone caught it at some point and said, no one's going to ever see it, so it doesn't matter.
Yeah, whatever. Yeah. But that was like a small detail that you only see when you look at what's on the disc. It's like, yeah, okay, here's the thing.
You know, it would have been fun if one of the programmers put some sort of Easter egg in here. And so where the map changes somewhat with a name or something on there to kind of, hey, no one will ever see this unless you go and dive into the assets like you did. That's so cool.
And here, like the cross here now, when you go up, it's all forest.
Yep.
So that's interesting one. And yeah, so I did all, like I said, I extracted them all because I could.
Yeah. You got them all.
Yeah. Now for the dungeon, it's a different story. The dungeons, it's a bunch of mini maps.
Yeah.
And here are the various mini maps. So at least those I could find.
Yeah, and these are the individual rooms that you access, and in between those rooms you have kind of a first-person dungeon crawler kind of a view.
Yeah. You have the various hallways and stuff, but yeah, so these are the main, because the dungeons are probably much larger, and also not just larger, but also with a lot of empty space.
Yes.
So storing the whole thing would not be very efficient. But this is all the thing I found. On the disc were all, and once again, I'm sure you've recognized many of those.
Oh yeah.
Or if not all. So this is awesome. So Ultima itself, I mean, for
simple game, fairly simple.
I mean, it's something written for the Apple II, so we was not going to push the limits of the ST, but it's still interesting. I found it fun to recover all the maps and all the assets from the disc, and find the little bugs, quote unquote bugs, that you would never notice otherwise.
No, and it's interesting to see how again, back to the point earlier, is how they change depending upon the game that's being coded for, what tools are being used. A lot of the same tools are being used, but there are different tools used in different cases.
Oh yeah. So yeah, and that's pretty much a rundown of some games. Like I said, not all of them. There were some, like which one I looked at. Wings of Death does not really bring anything more, and especially I was disappointed by the blitter version, because the version that works with the blitter is not faster, does not like...
I don't notice much difference. Yeah,
so
exactly. I love Wings of Death, and that's a game that, had I known about when I was younger, I would have loved, because it runs really nicely, but the fact is the blitter didn't do much to it. No,
it did not. So that's why I chose those games.
Excellent. Wow. I mean, this is amazing, and it's just so cool to see how you deep dived into all these games, these specific examples, and started extracting it out and learning, reverse engineering effectively what was going on there.
Pretty much, yes.
Yeah. Oh,
yeah.
awesome.
So it's I mean, it's interesting. As I said, limitation brings creativity.
Yeah.
And you'll find that on the ST and on all systems that they will need to come up with their own tricks and ways. And the hardware guys say, here's how it's going to go. And the software guy says, yeah, no. We'll push things, or what if I do this? Can I push things more?
Well, so something to think about. I mean, have you looked at many of the demos? The demo scene at all?
Demos I've not looked, no. They are... The reason is because it's much harder to make a game than a demo.
Oh, yeah, absolutely. I mean, the demos are very, just you run from start to finish, right? And it's not like it's not interactive at all. Or some of them are a little interactive, but not tremendously.
But you control exactly what you're doing.
Yes.
And yes, so it's... so I focused really on the games. Like I say, I've tried to do like the popular games and those who push the limit. But yeah, so that's the... So I've not looked at the demos. And yeah, the demos, they push it even further because they can and have lots of different things.
Oh, yeah.
But I'm always amazed when they're able to push the limits while doing it an actual game.
Yes. No, well, exactly. Making it fully interactive.
Yeah.
Back to that point earlier, right? So if you're needing game code to be running simultaneously at the same time, you have to be even that much more efficient, right?
Oh, yeah.
Yeah.
Because you cannot count for all possible scenarios, so you need to know, you need to account for a lot of things.
Yeah, because you may move the character one to the right or the left or any other direction potentially, yeah.
Or all of a sudden there is slightly more things on the screen, and so it would, like frame rate would drop or thing like that. So, yeah.
Or how to account so that it doesn't drop or to minimize the drop.
Exactly.
Yeah. Well, thank you so much again for the time. It was really, really enlightening, and I think a lot of people will really be excited to see this and understand how this actually works. It's fascinating. It's absolutely fascinating, especially taking a relatively limited system like the Atari ST. I love the Atari ST. It's my favorite. I'll be the first to say it is more limited, but it's amazing what people are able to do with it, nonetheless.
Oh, yeah, absolutely. Absolutely.
Fantastic. All right, well, I appreciate the time, and we'll keep in touch as always. All right?
Okay.
Good to see you, Laurent. Take care.
Yep.
Cheers.
Bye.
Bye-bye.
I want to thank ECDHE. Thank you so very, very much for taking the time to go through this amazing lesson and how the Atari ST graphics work, and the reverse engineering that you did in order to understand some of the tricks that were used on some of these more complex games. Dungeon Master Ultima V, relatively simple, but still some cool stuff to learn from it. And not only did he do it once, he did it twice, because the first time, well, yours truly ended up messing up the audio. So big thanks again. I learned a tremendous amount. Hopefully you did as well, and hopefully you enjoyed the content. All right, thanks for watching, and have a fantastic day. Later.